Okay. So hello, everyone. Thanks a lot for coming for this talk. My name is Lohit Vijay Renu. I'm a software engineer at Twitter. I also have my teammate Gara with me. So Twitter has been running Hadoop for quite some time. For the past close to 1 year, we have been running Hadoop 2 in production. So this talk is about our learning and experience in moving 1,000 users and multi-petabyte workload from Hadoop 1 to Hadoop 2. What are our future challenges and our contributions? So like Twitter, as you know, in the past few years have added like lots of new features. Pretty much all the new features or the organizations have Hadoop as their offline batch processing system in some or the other way in their pipeline. So it ranges from personalization, growth, analytics, revenue. So they have like various different kinds of workloads running on Hadoop. The recently announced Nielsen Twitter TV rating also uses Hadoop in a way, even though it seems like it's a real-time tweet impression. They use Hadoop with the tight SLA jobs. So not just compute. We also use HDFS quite a bit for storage. We store lots of raw logs, MySQL, and Manhattan. Manhattan is our internal key value implementation. Git and SVN repository all are backed up to HDFS. So supporting this various different kinds of workloads and SLAs requires a complex setup. So this is our Hadoop multi-cluster and a data movement pipeline setup inside a DC. So we have multiple DC, and the setup looks very similar to this. So what we have towards the very left is the Twitter front-end servers. So they generate like lots of logs, and we use Scribe to send those logs to something called a Hadoop real-time cluster. So the requirements, like the SLA requirements on this cluster is like very high. So we always control like the number of users, the type of applications on this cluster. I remember that this cluster has been up and running without any problems for more than a year, no downtime at all. And this cluster is also used by a lot of our search indexes, ad shards to bootstrap data out of HDFS. We also have a setup where we have like a HTTP server in front of the HDFS, and we serve out live user data out of HDFS in some cases. So since the data retention on this cluster is only about 7 days, before getting deleted, what we do is we copy the logs using our self-service data movement pipeline to something called a Hadoop processing cluster. So Hadoop processing cluster is like our production cluster. So only jobs with approved capacity and which has already gone through like rigorous testing, they run on the processing cluster. So like for example, the daily, hourly, or weekly jobs. So the results from those processing are usually fed back to the real-time cluster to be consumed by the searcher ad shards, or even partners, or sometimes even loaded into Vertica for analytics. So the retention policy on this, the data retention policy on this cluster is about a month. Before deleting the logs, what we do is we copy the raw logs as well as the important process results to our data warehouse cluster. So the retention policy on the data warehouse cluster is about 6 months to a year, but it's like not an infinite storage. So what we do is we go and take a look at all the data which has not been accessed for few months, and we automatically move those data to a Hadoop cold cluster. If at all users need to access that data sometime, so we either copy it back, or we request the users to run a job reading the data from a different cluster, but within the same data center. So warehouse cluster is like our ad hoc cluster. Users run lots of experimentations and queries. Apart from that, we have like a bunch of test cluster where test logs are in there, and people can come and test their jobs before even deploying it on the warehouse cluster. So for the storage, we also have like the MySQL, Manhattan, and SVN store the data in the backup. Sometimes we also back up data from the warehouse cluster. And we also use HBase. So we load the data from our MySQL tables into the HBase so that the MapReduce jobs can access the data from within the HBase. So having this complex system poses like a different kind of challenges and scales. So unfortunately, I could not give like the exact numbers, but we are looking in the order of something like we have today tens of thousands of Hadoop servers, like a mix of hardware, depending on the use case and depending on the cluster type. Like we have hundreds of thousands of disk drives. We store few hundred petabytes in HDFS as of today. And we run like tens of thousands of daily Hadoop jobs and crunching tens of petabytes of data. And those Hadoop jobs in themselves have like tens of millions of tasks. To give a rough estimate, like an individual cluster stats looks something like this. So a cluster, we have multiple clusters which have more than 3,500 nodes. They store anywhere between 30 to 50 petabytes of data on HDFS. Our name nodes peak to 35,000 RPCs per second. More than 30,000 jobs run daily with more than 10 million tasks across the entire cluster. And these clusters typically crunch more than 6 petabytes a day. So with this scale, you can imagine the challenges we face with scaling a Hadoop within Twitter. So dialing back the time, sometime around Q4 of 2012, right? So what we had is we had like lots of Hadoop clusters already running in production, but all of them were in running Hadoop 1. So the challenges with that was like many of the teams, pretty much everyone across all the organization came and told us that they need to grow their Hadoop needs by 2 to 3x, right? So we had a huge scalability challenge. The name nodes at that point, our biggest cluster, the warehouse clusters, we were already storing 250 million objects. We were running with a 96 gig heap. So if a name node goes into a full GC or any GC kind of process, it would affect the entire cluster. So not just the name node, the job tracker also had a lot of scalability issues. For example, I'll give you one example which we always see. So the job tracker has this property to cache all the job as well as the task status in memory. And that is configured to X number of jobs within a, per user. If a user, it doesn't take into account the size of the job. Like if a user run like 50,000 map tasks, which is very common for us. And if there are enough users like that, what we used to happen is job tracker would go into like a full GC cycle all the time. So to work around that, what we had to do is we had to submit like one map, one reduce job, sleep job for the same user, flush out all the things which are cached by job tracker and bring back job tracker to functionality, right? So that was a major issue. And reliability, of course, was a major problem for us. For example, we know that even though Hadoop is viewed as like a batch processing system, the SLA requirements were pretty high on our clusters. We always see cases where people come and say that, okay, we need to run our job within an hour. So this is our tight SLA. But the job in themselves, without any problems, will take 50 minutes. So even if there are like a bad node or anything, so we still have like problems. So downtime was a major concern. So not just like an unplanned downtime, even on a regular maintenance, restart of a name node was a major issue for us in Hadoop 1. So because it was storing so many 250 million objects, so we used to see always this problem where if we lost like 2 or 3 racks out of 40 odd racks, the name node would go into like a re-replication loop, which would lose data nodes which had already been registered, and the name node would never come back. While this is happening, we also had, apart from the MapReduce load, like people access our Hadoop cluster externally, so like search and other guys. So we had to shield them to say that, okay, don't bother me until the name node is back up. So we used to put like IP table rules around the name node, let the name node come back up, and then open up the cluster for business, right? So the efficiency was also a major problem. I'll show in the graph where the job tracker was, even though like there were like lots of workers, task trackers, it was not able to efficiently assign slots for the task trackers, right? Above all, like maintenance was a major issue for us. So we used to see some problems. We say that, okay, this is how we fix it. And later to realize that this had already been fixed in the upstream like a newer version of Hadoop, right? So maintaining like old code base was a big issue for us. So that's when we decided that, okay, so if we were going to build like the new clusters, it would be like a Hadoop 2 clusters. And from the very beginning, we decided that we won't bother about upgrading the huge clusters in place from Hadoop 1 to Hadoop 2. What we'll do is for a while, we'll support both Hadoop 1 and Hadoop 2 clusters, and then slowly migrate users to the new one, so that they can still run on the Hadoop 1 until we stabilize or productionalize the Hadoop 2. So this was an initial configuration we came up with. So we talked to a lot of folks from the community, Yahoo folks, Hortonworks, Cloudera. So they gave us a good idea that the resource manager should be able to scale to a couple of thousands of nodes. So what we decided was, for all the worker nodes, we decided to have like a node manager and data node on them, and the resource manager would spawn across all the worker nodes. But for name node, we decided to go with the federation. So we had, from our previous experience, we knew like a different kind of access pattern for a different set of data on our HDFS cluster. For example, there were a bunch of shared logs which the data movement pipeline used to copy the data, copy the logs from one cluster to another. So these are like big files with big blocks, and these are like read-heavy kind of logs. While on the other hand, the temp directory or the temp namespace used to be something like, we run like a lot of pig and scalding workflows. The intermediate MapReduce output of those workflows are actually stored on HDFS, right? So these are like high churn, like very small file, lots of small files. So the access pattern for them is a little different from that of logs. And users, of course, we carved out a different namespace. So we decided from the very beginning to go with the federation setup. The idea was like, tomorrow if you want to add more users to the system, so you could add like a new namespaces. Or if you want to scale the cluster for like lots of dynamic or short-lived kind of workload, you could add more temp name nodes, temp namespaces or something like that. We also decided that, okay, we will be running HA for these name nodes. So each of these namespaces had 2 active and standby, and all of them use journal nodes. So with our initial configuration, we had like 6 name nodes, and all of them were running journal nodes on them. This picture shows that each name node was configured to use 3 journal nodes, but right now we are running with 5 of them, so that the idea is even if you bring down a namespace, the other namespaces are up and running. From the very beginning, we decided that none of these namespace magic should be like exposed to user. Like if a user comes and says that, okay, this is a cluster, he should see only a bunch of directories in them, right? So that's why we decided to add like a view file system layer for the users. And balancer, like lots of our admin tools, like HRaven is one of our open source tools, and metrics and alerts was configured on the entire cluster, right? So with this, like initial configuration, we decided to do the migration in steps. So it looks something like this. In the phase 1, we did like a lot of testing. Phase 2 was semi-production, and phase 3 is like production, what we are running today. We started off with Apache 2.0.3. At that time, this was the latest branch. What we did was we forked this branch internally because we wanted to make a lot of fixes and then also contribute back to the community. We went with a new OS, new Java, and also new hardware. So yes, last year, Hadoop Summit, Yoop and Jay from Twitter, they gave a talk about Twitter hardware, Twitter Hadoop servers. So I have a link at the bottom. I encourage everyone to visit that. So basically, it talks about like smaller 1U boxes, which are much more performant and cost effective. So we decided that, okay, we'll build this entire stack with new software and hardware and run like lots of benchmarks. So we ran like pretty much all the benchmarks we knew: TerraGen, TerraSort, GridMix, PigMix, lots of user jobs. I remember like when we retired this test cluster, we had already run a couple of 100,000 test jobs on this cluster. So we used to constantly keep running jobs, and we used to go and fail over the name node, kill the data nodes, see how the failure is happening, and all sorts of things. That's when we also started updating a lot of our dependent components like pig, scalding, cascading, our internal libraries called elephant bird, lots of our admin tools. So all those things we started updating and made to work with Hadoop 2. And also the data movement pipeline was made sure that it could work across Hadoop 1 and Hadoop 2. In the phase 2, like once we were ready and we were like pretty confident, what we did was we built a massive, more than 1,000 node Hadoop cluster and asked one of our revenue users to run their job in parallel on both Hadoop 1 and Hadoop 2, right? So we had set up like lots of alert metrics. We use our internal tools to set up all these metrics. So if a name node does a failover, we need to be notified as to why that happened to see if there is any problem or any bug associated with that, right? So we had like all that in place, and that's when we started seeing like lots of improvements, tuning parameters, lots of bugs we discovered at the early stage in the 2.0 branch and started contributing back to the community. So the community was also moving forward in parallel. So we used to like backport many fixes or contribute back. So Gera, in the second half of this talk, he'll go into the details about like all the issues we saw and how we fixed it, right? So users started seeing like lots of benefits when they see the same job run on both Hadoop 1 and Hadoop 2, and Hadoop 2 was performing better. They immediately realized that, okay, this is like a better cluster. So in phase 3, what we have now is like, in parallel, we were also developing and then up-revving the branches. Like we have a 2.05, like a production branch with like hundreds of fixes and backports on top of it. So this has become our like a very stable release internally. We have like a template to roll out new cluster, all the Puppet configuration, the cluster configuration. I know that our SREs or sysadmins can now roll out like a couple of hundred nodes of cluster within half a day. So everything is set, and then we can like create clusters very fast. And now, as a development, what we are doing is now we are at a 2.3 branch. We have deployed it on like our test cluster. What our goal is, the community is at 2.0 release, right? So our goal is to contribute all the patches we have done, all the fixes we have done to the upstream so that we don't have to keep this internal fork for a long time, right? So having done all this, so this is how it looks like. So the top one is a Hadoop 1 cluster. Both the cluster shows both the graph shows CPU utilization of Hadoop 1 and Hadoop 2 cluster. Both of them were pretty much full. You can see that the CPU utilization for Hadoop 1 was like peaks of 45%, while in Hadoop 2 we see about 85%. So this is not just Hadoop 2, but a combination of our hardware as well as like lots of job optimization, because we squeeze a lot of tasks now based on like the memory requirement. Earlier, Hadoop 1 had like a fixed slot, right? You can only say that, okay, you can have only say 10 mappers and 5 reducers on a machine. But with Yarn, it gives you a flexibility to change and play around based on the job, right? So this is how our cluster look for an entire day. And the memory utilization, you can clearly see that the job tracker was not able to scale or schedule tasks efficiently on Hadoop 1, while in Hadoop 2, you can see we are pretty much pegged. There are still room for improvements. Ideally, these memory utilization should be 100%. But there is some improvements around resource allocation, reservation, and how quickly the fair scheduler can allocate and do resources, right? So this is how it looks today. This has been like really helpful for us. So now Gera will give details about the individual problems we saw and how we fixed it and where we are in committing back those to the community. Thank you.
Is it on? OK. So first thing, since we had to maintain multiple versions of Hadoop at the same time, it usually boils down to using web-based file systems typical usages are web HDFS and HFTP. Because we already used HFTP for cross-data center log mover, we went with that file system. After we started using jobs in production, some migrations were partial, so occasionally we had to consume data on Hadoop 1 cluster that was generated on Hadoop 2. And immediately we saw problems that do not occur with typical DCP-based jobs. For example, when computing splits, the elephant bird relies on catching file not found exception and wasn't thrown for open calls on non-existing paths. We also had to fix a bunch of bugs regarding cross-version checksum verification. So that allows us to make sure that data that we push between versions is correct. Also, we have a lot of homegrown problems. Our user base is huge. And we have a lot of pre-existing scripts. And the common convention at Twitter is to use canonical URIs to refer to the clusters. And so when you use view files, I mean, you don't have the view file system. And on the Hadoop 2 side, we don't have a canonical representation for all possible namespaces. This is hidden by the view file system. However, since users hardcode HDFS, we had to transparently change HDFS implementation that maps to view file system transparently. And this allowed us to migrate jobs without changing the source code. Otherwise, we had to wait a long time until all users moved to the new convention. And furthermore, users are just used to typing the full URIs. So we just decided pragmatically to help them along the way. Similar problems arise with the high availability setup. Even if you know the correct location of your name node, it might be in the standby mode. In that case, it's not able to serve any metadata operations. We could have solved, there's no real solution without coding, but we didn't want to provide any additional failover logic on the Hadoop 1 side because we wanted to cut maintenance costs on the Hadoop 1 side. So what we did instead, we implemented redirects transparently. We loaded actually our canonical view file system on the server side. View file system is the client side artifact, but we load it on the server side in the name nodes, and name nodes know how to redirect requests correctly, first based on the namespace, and then when the right namespace is hit, it looks how to redirect to the active name node if accidentally the standby name node was hit first. The drawback is, of course, that standby name node has to be up all the time, but that's what we are striving for anyways, and we have alerts set up for this. As Lahid mentioned, maintaining both versions incurred a large cost of recompiling multiple projects that we use, like peak, cascading, scalding, elephant bird, Hadoop, LZO, and so on. Many bugs were encountered and fixed. The only one issue I want to call out here is with the H-Raven that allows us to monitor performance of the jobs over time. There is a transition of there is no type-based slots in Hadoop 2. So we need to transparently translate type-based slot milliseconds to megabyte milliseconds in Hadoop 2 if we want to compare performance of jobs between Hadoop 2 and Hadoop 1 clusters. Once we started taking things into production, we started discovering a lot of bugs. So it turned out you can't use ViewFS for public files in distributed cache, and we actually need it for our project Woodpecker that I will talk about later. Once we fixed this problem, we encountered RPC storms on our name nodes when node managers verify whether a file is public. And So there were minor issues with just expected user experience. In Hadoop 1, you can see user-specified status string, whereas you cannot see it in Hadoop 2 and UI, so we fixed that. We also embraced Uberized jobs to schedule small jobs efficiently on the cluster. However, there were also problems associated with that. Then typical incidents where one job can pollute the whole cluster with excessive logging. Then we started capping the log for the user logs, and this feature was not working for us because the tail of the log was always lost. It's cached in the JVM memory, and whenever the JVM crashes, it doesn't flush it. So we fixed that. We invested a lot in improving diagnostic information around our jobs. Specifically, users always complain why something is killed. And so we allow specifying custom diagnostic messages. The frameworks can also use the same API. So DAGs can notify why the specific job in the DAG was killed. And AppMaster also notifies, provides additional diagnostic information for kills based on speculation or reducer preemption when mappers are rerun. Specifically, also the user convenience, when you come back in the morning and want to see why the job is stuck and was killed, the users usually don't see the thread dump, which is the most valuable information in such a situation. So we now create thread dumps automatically. It was actually at some point in one of the Apache versions, but for some reason it disappeared in Hadoop 2. Similarly, we do the same, allow the same users to do on demand whenever they feel that something is wrong with their job. We did a bunch of improvements, at least that make sense to us, across web UIs, added additional statistics, added easy way to determine whether a job is big because how much memory it took on the cluster, various filtering functions. Once we adopted, once we started running large jobs on Yarn, we saw interesting challenges with reliability. Specifically, I want to call out the dealing with unhealthy nodes. Currently, Yarn actually tends to kill all the containers on the node manager, and then you can imagine if these containers were the cause for the node to become unhealthy, when they wander around, they keep making cluster worse and worse because now they land on the node manager even in higher density. As Wahid mentioned, because we were early adopters of branches, so we saw multiple issues with resource manager crashes. Sometimes we were the first to fix them. Sometimes we were able to benefit from the community because it was already fixed there. So it was great. We also, to achieve higher computational density, we made sure that we can tune jobs individually based on the business case, because not every job needs the same size of container. But for users, it's a painful process because they need to know that there are a lot of correlated parameters that has to be set in the same time. And sometimes they forget it, and the result is either the job is killed because more memory is used that you allocated for the container size, or you wasted a lot of memory because you increased the container size but forgot to set a high heap. Also, our users move fast-paced and like to use newer versions of the frameworks that Hadoop depends on. And so, for example, you probably all know that Guava is very outdated in Hadoop. But many of the jobs use much newer versions, features of the newer versions. And Hadoop MapReduce 2 has actually a very elegant feature that allows to isolate job classes from the framework classes called job class loader. And so we started embracing it. However, we encountered a bunch of bugs around there and fixed them. Overall, we try to educate our users how to debug issues themselves, so they know how to get thread dumps. We get heap dumps on out-of-memory exceptions in the same log directory when normal logs are stored, and then they are aggregated together with typical your syslog, stdout, and so on. So we run our applications in multi-data center environments. Of course, we try not to run jobs across the data center, but sometimes, even without knowledge of the users, it happens that they have to submit jobs across the data center. And there is a considerable delay in the split calculation if you have to process a lot of files. So for this reason, we simply moved the split calculation into the app master. We also needed to differentiate quality of service between client-server traffic and server-to-server traffic in our data centers. And we achieved this by using DCP bit coloring on server sockets. And it was quite an easy change in HDFS, but turned out to be challenging with HFTP because it uses HTTP URL connection. Yeah, so we actually switched to Apache Commons HTTP client for that. We also implemented data transfer, so that is HDFS client-side throttling. So I guess I have to rush through many slides here. So we started adopting frameworks beyond MapReduce, as people say now. Some of them are actually not truly beyond MapReduce. For example, Wobbit is a machine learning library that is already implemented on top of MapReduce, but it required an additional step of spawning the spanning tree. So it's quite an inconvenient. We simply put the step into the app master. It's now launched as a single package. Also, our analytics infrastructure team looks into Spark, and they already run experiments on our test clusters on Yarn. So one of the bigger projects that we do right now at Twitter is truly shared cache, externally referred as Woodpecker. It just comes out of realization that while MapReduce concepts of function shipping computation to data is a great concept, but sometimes it's just too much, and we don't coordinate well shipping shared artifacts, deploying shared artifacts across teams, and what ends up happening that same jars are localized over and over again between workflows. And this means that sometimes for an HDFS split, which is 512 MB, you ship 600 MB of jar artifacts. So this project identifies each jar by its SHA signature, and the client then can know whether it's worthwhile to upload this jar package or it's already there. This has another positive effect then, because all jars are uniquely identified in the whole environment. The localization cost is shared across all the jobs, across all the workflows, regardless how they arose through scalding or pig. And of course, we added counters and metrics that allows us to measure the success of it. As we had mentioned, now what I described now was our way to productize Hadoop 2. Now we're in the process of taking new steps, and we need to grow our clusters because the complexity of adding new clusters just doesn't scale. So we will end up with clusters of more than 10,000 nodes very soon. And for this, we had to test scalability of name node resource manager, experiment with heap sizes, and garbage collection strategies. We looked at various other issues. The biggest challenge probably will be, or one of the biggest challenges will be the startup of the name nodes after total shutdown because of the long initial processing of the block reports. Future work ideas include, finally, to productize Resource Manager, HA, and work preserving restarts for both resource managers and node managers that are already available that will allow us to upgrade much more frequently. We're looking into utilizing our standby hardware by using standby for read-only workloads. This is similar to what's done in the database world. Then we will look at how to create virtual subclusters that have affinity to certain namespaces, but based on the business case. We're looking in all kinds of JIRs that allow more scalable name node when you split off services or separate block management from the namespace management and so on. So one thing I wanted to mention was we're looking also at the concept of the fair share for RPCs. So similarly how we do fair share scheduling in Resource Manager, we want to share RPC throughput fairly between different tenants in the name node for name node metadata transactions. So summary, we feel that we were successful in our transition. We removed the job tracker bottleneck. We achieved much higher computational density with flexible slots. We reduced name node bottleneck by using federation. Having HA for the name node is great because now you can experiment with different parameters on the standby name node, fail over, see whether it works. If it worked fine, you keep it. Otherwise, you simply fail over to the name node with the old configuration. We're now much closer to upstream, which allows us both to consume fixes from outside much quicker and contribute back. And we really like that we can embrace new frameworks. So at the conclusion, you probably have seen that migrating thousands of users and lots of source code is anything but trivial, but Hadoop 2 made it worthwhile, and because we now have much more efficiency and reliability. So we greatly benefited from the community fixes, and we were able to contribute back as well. And I would like to thank you for your attention, and we will be able to take some questions right now, but we're also happy to chat with you in the hallways.
Thanks. Yes.
Just out of curiosity, how many engineers on the Hadoop approximately?
Thanks for this question. That allows us actually to make sure that we acknowledge that it's not just the work of us two, it's the work of the Hadoop team that sits in front of us. And what would you say? In low tens?
Low tens. Yes.
When you showed the comparison between the Hadoop 1 and 2 for performance and utilization of the different hardware, how did you normalize the slide? I remember your new cluster is the H3, your old one is Westmeer, and there are a lot higher blocks and a lot more memory.
Yes. So the question was like when we showed the graphs comparison between Hadoop 1 and Hadoop 2 for CPU and memory utilization, how did we normalize, right? So basically the idea was like if we were to deploy this, like the users, what they view the cluster as a capacity in terms of nodes, be either it like the number of slots or the disk space capacity for our users, right? So it doesn't matter if it was on a different hardware versus new hardware. We came up with like a scale, like the old hardware versus new hardware was 1:1.5. Even though like the old one was like a 2 U boxes, the new one was like 1 U box. So all these details are in the talk which was there in the previous year's presentation. So then once you deploy, you want to see the utilization, right? Like because you have already given away that capacity to the users, you wanted to measure like how you are utilizing those. So that's what the slide was showing you.
But your new hardware is a lot leaner.
Yes. Yes. So that's.
How much is the hardware? How much is the software?
So we don't have that comparison right now because we are also running Hadoop 2 on the old hardware, like as we phase out old clusters. So we could not get that information right now. But yes, it's a combination of both hardware as well as the platform in themselves.
15 seconds.
Yeah, we can take one more last question, sorry.
So I very like moving your temp file system to a different namespace in the federation path. So I was wondering how much was the performance benefit given that it's a temporary file system?
Okay. So the question was he liked the way we set up a different namespace for temp, and he was saying how much benefits or performance improvement we got, right? So this was actually very good because in Hadoop 1 cluster, the entire load used to come into one name node. We could not come up with like an explanation as to who is doing what, right? So we had to develop this tool called name node top. So what it used to do is it used to sit and watch the audits, and then just like a top for your Linux system, it will give you a stats as to which user is making which kind of operations, right? So we had to come up and then say that, okay, this temp is really hit, but the number of files on them are not that much. So by offloading that, now all our clusters are running pretty healthy. Another example I can give you is our Hadoop 1 cluster name node heap was about 96 gig. Right now, we are running all our name nodes within 31 gig heap to take the compress pointers of the JVM. So that has been running pretty good for us. Yeah.
That's it.
Yes, that's right. So unfortunately, we are out of time, but we can take questions offline. We are around the corridor.